Okay, 3 kilogram block is initially sliding across the frictional surface at 5 meters per second. Determine the initial momentum of the object. So P initial equals mass times V initial. Initial momentum. So it's the first time just calculating the momentum. So 3 kilograms, that's your mass. V initial is 5 meters per second. So 3.0 kilograms times 5.0 meters per second. So that's an initial momentum of 15 kilograms times meters per second. Okay. All right, so let me draw a picture here. Sliding along. V is positive 5.0 meters per second. 3.0 kilograms. All right. Plus 1.5 Newton force is applied to the object for 5 seconds. So some force comes along, and it's 1.5 newtons in the positive direction. So if it's already moving in the positive direction and the force is in the positive direction, it should speed up. All right, determine the final momentum of the object. So remember, change in momentum equals impulse. All right, which equals force times time. Okay, you can't do m delta v to find the change in momentum because we don't know the final velocity. So we got to use force times time to find the impulse given to the block by this force. So that's going to be plus 1.5 newtons times 5.0 seconds. 5 times 1.5 is about 7.5. All right. So the impulse given to the block is plus 7.5 Newton seconds, delta P. So your P final, it's got to be equal to whatever your initial momentum is. This is a lowercase p, so I try to remember to put that little tail on the front of it. Not capital P as in power. So P final has to equal P initial plus whatever the change in momentum is. So it was 15. You'll notice the units, kilograms, plus 7.5, all right? So that's going to be 22.5 kilograms times meters per second. Like I was going to say, the units here, these two units are equivalent, so we can just add them together, and I can pick the unit I want on it. So that's the final momentum. Okay, the final speed of the object. Well, P final equals mass times V final. So if I know the final momentum is positive, and this should be positive, positive 22.5, and I know the mass is 3.0 kilograms, I have to solve for V final. So then I divide both sides by 3, so positive 22.5 divided by 3 equals V final. V final equals should be about 7.1, 7.2, 7.3, something like that. 7.5 meters per second. It would be kilograms meters per second divided by kilograms. Kilograms will cancel, and you end up there. So this is a multi-step process that I just did. You know, initial momentum is this much. The change was initial was 15. We gained 7.5 units of momentum from the impulse, from the force, which made the final momentum 22.5. Final momentum 22.5 equals the mass of the object times its final velocity. So to give the object a final momentum of 22.5, its speed would have to be 7.5. And it is positive. It's in the positive direction. All right. 2 kilogram block sliding to the left across the frictionless surface. So a similar diagram here. 2.0 kilograms. Its velocity initial is 15 meters per second. All right. Force of 4 newtons pushes on the right side of the block for 10 seconds. So the force is pushing on the right side. So if it's pushing on the right side, right? If it's moving this way and the push is that way, this object's going to slow down. So this means the change in momentum will be negative, right? The momentum will have to go down because it's slowing down. But anyway, for 10 seconds, okay, time of the push is 10 seconds. That's quite a long time. I bet this is going to cause the block to turn around and head the other way, actually. Determine how fast and in what direction the block is moving after the force is applied. Draw a picture to help. So, this is a situation where I'm gonna write everything down in a big list here. Since it's pushing on the right side, the force is going to be negative 4 newtons. This direction matters here. This is our first time having a negative force. Final, we don't know. Mass is 2.0 kilograms. What I'm going to do is, rather than breaking it up all in different steps, I'm going to go right to the fact that force times time has to equal mass times change in velocity. All right? So, what I'm looking for here is the change in velocity. I know the force is negative 4 newtons. It's going to apply in the negative direction for 10 seconds. So it's negative 4 newtons for a time of 10 seconds. I know the mass is 2.0 kilograms. I could even put in V final minus V initial here, but it makes the algebra quite a bit more difficult. So I'm just going to put in delta V there. I'm going to solve for delta V. So you might remember to solve for delta V. Negative 40 newton seconds, multiply those, divide both sides by 2.0 kilograms. All right, 40 divided by 2 is negative 20, is the change in the velocity. So the velocity here is changing by negative 20. So if it started at 15, right? So V final is going to be V initial plus whatever the change is. That's not an equation on your reference sheet. That's just a general concept. I used the same thing up here where I said, okay, your final has to be whatever you started at plus whatever the change was. Your final has to be whatever you started at plus whatever the change is. So V final is positive 15 meters per second plus the change, which is negative 20. The change is negative 20. So your V final actually ends up being negative 5 meters per second. So this force, this could be like you threw something and there's into a fan or something. You threw something in at a fan. The fan's blowing on it. So it's going to slow down and then it's going to start going back the other direction. So we've hit the point where that force has actually stopped it and is now turning around. This is what gravity does when you throw something up in the air, right? The force acts down the whole time, so it slows down on the way up, stops, and then it starts gaining speed on the way back down. So, pretty cool. It ends up being a final velocity of negative 5. A couple more minutes here. Just this one I want you to try to do first. I think I'll, well, you know what? Let's go ahead and take a look at this one. Baseball bat has a mass of 1.145 kilograms. Fastball pitches around 40 meters per second. Typical line drive leaves the bat at 49. According to research, the average time of contact between the ball and the bat is about 0.7 milliseconds. Okay, what's the average force applied by the bat? Well, force times time equals m delta v. So I'm jumping right to that step. But let's be careful here. Let's draw a picture. All right, so before, you got the batter looking that way. Softball player maybe. Ball's coming in, right? The initial is 40 meters per second. But then, ball player puts all their energy into it, right? So this is, they've hit the ball, and now it's flying away. The final is 49 meters per second. Ball's flying away the other way. So the ball's come in, bat has hit it, right? And the ball's flying away. All right, now, direction matters, all right? And I'll show you why in a second here. So the average force would be mass times change in velocity over time if we divide both sides by time, right? So the mass here is 0.145 kilograms. Now how about the change in velocity? What's a change in velocity? Remember, change in velocity equals v final minus v initial. Okay, so it's 49 minus 40, so it's 9. That would be wrong. You have to put in the negative sign on this because this velocity is actually changing by quite a bit. It's going down by 40, and then it's gaining negative 49 as it rebounds. So the change in velocity here is actually negative 49 is your final velocity, minus v initial, which is negative 40. Your change of velocity is actually negative 89 meters per second, the way I drew it here. It's really important. It makes your answer 10 times different, right? If the change is only 9 meters per second, then it would have to still be moving forward. If you hit it and you only hit it that way and you only changed it, it'd almost be like it went through the bat and it slowed down to 31 meters per second. That wouldn't make sense. So the actual change of velocity is negative 89 meters per second. The time is 0.7 times 10 to the negative third seconds. All right, so you can plug that into your calculator. And the negative sign here isn't that important, believe it or not, because the average force ends up being negative 18,000 newtons. All right, and this we'll talk a little bit more about in class. I don't want to give that away quite yet, but the answer is no. The ball flexes, believe it or not. The ball and bat flexes, like a spring. So what actually happens is you get a nice big peak here. Got a cameo appearance by Mr. Giampaolo here. Paolo. You get a graph that looks like this. The force peaks and it goes down. All right? Anyway.